Alrighty, hello everyone and welcome to Handmade Hero Show Recode Complete Game live on stream. We did, yesterday, we changed our lighting to now be able to iterate over sort of a hierarchy during its raycasting. And we now have to build some kind of a hierarchy, because what we did is we made the simplest possible hierarchy, which is just one node that contains all the other nodes. So now what we want to do is make something that will create an actual hierarchy of nodes where that hierarchy will, hopefully prune the list a little bit. And then from there, we have to start working on how we're going to actually efficiently traverse it and all those other sorts of ancillary concerns that we're going to have once we get to that point. So let me first just bring you up to speed on where we are. Excuse me. If we go through here, and take a look, you can see that we've got sort of our, this is sort of flat face lighting that we're working on here. We're actually doing interpolation at the moment, and you can even see it sort of occurring, like in here you can see those color washes occurring as the lighting kind of falls off as we go down towards the bottom. What we haven't done yet is actually made any world generation code that knows how to put the interpolation points in. So we actually even have a system where we'll be able to get rid of this banding entirely and make that wall appear flat if we want to by just placing the points properly and putting in a post filter on the light. So we're in a really good place to make some really good lighting in a bit here. And I'm looking forward to that. But at the moment, our primary concern is speeding this number up. Why? Because even though this appears to be running at a reasonable frame rate right now, it's not 60 frames a second. It's more like 30 at best case. Which is not good enough for what we want to do. And second, the real problem is this is a toy scenario. Normally there'll be it's going to be a wider, more stuff here and more depth potentially to it, like 2 layers down and so on. And this number will fall off a cliff at that point because remember, it's n squared. So adding every additional element makes our performance significantly worse, not just a linear amount worse. So our real goal here is to really linearize that number, get this down to 60 frames a second, and have it so that we can have our full world size running through the lighting without hitting that n squared part of the curve that really tanks the performance. That's really all we need to do here. Once we're done with that, we're actually in position to just have the world generator output some really good lighting stuff, I think. And we'll start playing with that to try and get some nice lighting effects in there. Because we already sort of have, and I'm really happy with how this is turning out actually, we already sort of have indications that that's going to be good. I mean, you can kind of see some pretty interesting lighting effects happen, like you get sort of these blue tinges on things when you get the blue bounce happening, you get nice shadowing happening here, so as you come around corners it illuminates what you can see and so on. So there's just a lot of stuff I think we're going to be able to do, and furthermore, all of this lighting is like fully, it's not based on just light sources. Anything can be lit up here. We can have each individual tile can be lit and illuminating light and so on. So I think that's going to be a lot of fun to play with, and I think we'll get a lot of visual quality out of the game that'll be worth it. So I'm pretty happy about how this is coming out. But again, really, it's all for nothing if we can't linearize that n squared lighting, because we're just not going to be able to get it fast enough if we don't. Excuse me. And the problem there, again, is no matter how optimal we make our lighting calculations, if they're n squared, they're just going to be too slow, right? At the n that we're using, it just by itself, the n squaredness approaches the speed of the processor in a bad way. So it's not about, we can't say, oh, well, n squared's okay, because our n will always be small enough that we can optimize the core routines to the point where we can still do it. It's not that way. The lighting numbers will get too high, and it's just nothing. There will be nothing we can do about it. So off we go. And if you remember correctly, what we did is we already modified everything to take hierarchies into account. But what we don't do right now is actually ever produce more than one box. So here is our build spatial partition for lighting function. What you can see is all it does is call the split box function that does nothing, right? So what we want to do is we want to have this split box function do something intelligent, and then we want this add overlapping boxes call to go ahead and produce the correct split of stuff into those boxes. Okay, so that's what we want to do there. So what I'm going to do first is I'm going to say, well, okay, what we want to do is when we split a box, let's just say that when we split it, we produce a split that's even that's at a particular. Let's just say that all we're going to do first is let's split our boxes in a prescribed fashion. So, for example, when we call split box here, maybe we just always split along the x-axis, then the y-axis, then the z-axis, or something like this. So we'll literally just do something super stupid that doesn't actually try to find a good place to split. It just splits without regard for how good the split is in a predictable way as a way to start things off. So if we take a look at split box here, maybe what we do is when we do build spatial partition for lighting, when we call split box, we just pass down something that's like dimension index, right? And so what we do here is we say, okay, you know, we've got 3 different dimensions that we're going to want to do. You know, this is the x-axis, this is the y-axis, this is the z-axis, something like this. And I probably don't actually need this switch statement. I'm writing it out longhand first, but we'll probably be able to actually do this with indices in a second here when we look at what the code looks like, so probably not actually that bad. But what we need to do here is say, well, we've got a P for box A that we need to figure out, a P for box B, a radius for box A, and a radius for box B. That's what we actually need to produce here. And so then we can go ahead and add these. I'm going to make a function that actually adds a box. Oops. Or I'm going to try to anyway. Something like this. And when we add a box to the lighting solution, it's just going to push a new one on in exactly the way that it was doing this before. So it's going to add. This is the result here. And so what I can do is I can assert in here that we haven't overflowed our box count. And I guess we actually have an array here that we can use. This is a box table. So what we can do here is we can say, all right, we can go ahead and remap this box. When we remap the box, what we could do is we can add an address for this box into the box table. So solution box table results equals results. So it just maps itself directly in there, and off we go. Right. So let's see here. So yeah, there's a couple kind of messed up things here, which is that we have sort of a dual mapping of these things. We don't really need this part here. We don't really need to take up space in the main box area. So it's a little bit iffy. Let me just kind of show you what I mean. The way we've got this is it's a little bit tough. So I don't know, where's our box references here? So I'm going to put this up at the top here. So there's 2 separate things. There's box storage and there's box referencing, because we have 2 sorts of arrays that we're working with here. One stores the actual box data and the other stores references to the box data. And the reason we did that, because remember from last stream, is because we want to store continuous ranges of references to arbitrary boxes as we sort these things out. And this makes things a little bit confusing, so it might be nice to actually have a way to talk about them separately in a nice clean way. And so let's just go ahead and actually try to figure out if we can do this in a reasonable way. You can see we've got this one here. We probably want to do something like this, where we do, oops. So what we want to do here is say, okay, there's such a thing as adding a box reference, and that does not increase our box count at all. It just increases our box reference count, right? So there's a box table count, which is a separate thing, and then there's a box table, and those are not the same things, right? They're different things. And so in order to do something like that, what we want to say is, let's say that our box, or maybe we call this a box ref count. So we say that our box ref count needs to be less than the box table size. The result is going to be the box ref count incremented, and then we don't actually return any kind of a box itself. We're just going to return that reference. And what we do there is we say, all right, whatever the box is, so this is a box storage index, whatever the box index in the actual storage array you were trying to store, we're going to store that here for the result, and we're going to return you back where we stored it, right? So that add box reference there is what we're looking for. So then we have add box storage. Add box storage actually gives you a new actual box, and that's going to increase the box count itself. It's not going to it's not going to do anything with a reference to that box. It's just saying I'm producing new box storage for you, and here is the index for that box storage, right? So what we want to do here is say, okay, we've got the box count incremented. We've got the new box that we're going to give you. And, you know, actually, I guess we don't even need to get it. All we're doing is reserving a bit of that for you. So now what we can do is we can be a little bit cleaner about this. So, for example, when we go to build these things, before we were kind of doing this nonsense here with the like child count, truncation, blah, 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 and all that crap. We don't really want to do that yet, I don't think. What we want to do instead is we want to say, all right, let's go ahead and figure out what the child range is here. And let's say we've got, you know, first child index, and child count. So we've got a range of things that we're going to loop over here. And we want to go ahead and put those things, excuse me. We want to go ahead and sort those things into subarrays, right? So, trying to think of how we want to do this here, because this is pretty complicated, actually. The question is how we store these things while we're working with them. I'm tempted to kind of do this as a sort of a merge sort thing where we just swap indices around. Where we just have a buffer in place with all of the things, and as we go down, we keep partitions of stuff. And on the way up, we merge them back together. I'm kind of thinking that's a good way to do this. Yeah, I mean, let's think about that for a second, right? So if we were only doing this along one axis, so let's say we only did it along like the x-axis, it would be just a straight merge sort to sort everybody along the x-axis, and we could partition them as we merged. We could just bucket them into the number of buckets that we wanted from left to right, or any other way we wanted. Once you have them in that order, you know, you could do a second merge sort to do them in Y, and a third merge sort to do them in Z. It doesn't seem like a great way to do it, but you could. I'm going to push forward. I'm really not sure exactly how I want to write this. So I'm going to like kind of push forward a little bit on it and just see what's a reasonable way here. So we'll see, and we'll see how it goes. So what I want to do here is I want to be able to, first of all, let's use this call a little bit more wisely here. We'll use these two that we've got, right? So these are our 3 calls that we now have for working with boxes. In fact, you know what I might do is put them up here so they're easier to read. So that's how we get a box. Oops. That's how we add a reference to a box. That's how we store an actual box. Right. So that's relatively straightforward, and yeah, hopefully everything's fine with that. We could also just have a thing that allocates a block of box storage. I'm not of box referencing. Yeah, but I don't know exactly how we want to do that yet. So we'll take a look at that a little bit later. So anyway, if I go down through here and I go to my split box call, so when we do build spatial partition for lighting, before we branch into it, what I want to do is say, let's add box storage for the root box index. Like so. And assuming that we initialize this on entrance where we've got our box ref count equal to 0, then 0 becomes our root box index, which seems like a good idea anyway. We could even get rid of this and just know that 0 is. And we don't have to do any of this stuff. In order to get this box back, what we can do is say, all right, we want to get the box table. We want to get the box. Although, actually, no, sorry, this is box storage. We need to add box reference. There we go. So we're adding storage and adding a reference to that storage. Right. Then we can get that box back, and now we've got it. So now we have we can reference it, and we have it, which is what we want. We can then set it up. And I guess what we want to do here is say, well, all right, we've got this set of boxes that's in the box storage at the moment, and we want to be able to sort all of those boxes. We could also make it so that if we wanted to, our root box could just not have an index. So the other thing I could have done here, and maybe we want to do this, I'm not sure, is we could say that instead of a root box index, there's just a lighting box here, like that isn't included, that we just start on. And I don't know if we want to do that or not. That depends on whether we ever need to reference this box, which we probably don't. So we could actually get away with something like that. And maybe that's a smarter thing, because then that way box storage starts out without having any non-sorted boxes in it. I don't know. So I'm not going to do it yet, but it's just something to keep in mind. Yeah. So anyway, thinking this through. So then what I need to do is, the tricky part about this is we then need to start running over the boxes and partitioning them into split pieces that then themselves get further split. And in order to do that, it seems like I need to create a temporary array full of references that then gets sorted on the way down, which maybe that's the most efficient way to do it. I don't know, so we'll find out. Before we add this box, what I'd like to do is snap a copy of how many of these we have. Can change that to U16 since these are all U16s here. So what I'm going to do here is say first, actual box equals 0, actual box count equals solution box count. And so this is our range of actual boxes, right? Not including the fake boxes we're going to add for our, hierarchical, for our hierarchy. So when we come through here, I can then say, all right, this box's child count is the actual box count, and its first child index is the first actual box. And we are setting the radius to a faux thing that we know encloses everything. But if we wanted to, we could sweep, if we were going to waste time about it, we could sweep over the boxes here and look for the actual bounds. Maybe that's a good idea to do. I don't know. So let's actually create the bounds, because who cares? We're just playing around at the moment. So if we were going to do that, then what we need to do is a very simple process of bounds checking. What we need to do is say that the box position will just be the min p plus the max p times 0.5, so just the middle of that region. And the radius of the box is just going to be sort of that standard take the half of the diameter of the total min max p, right? So then if we want to find the the bounds of that, we just say v3 min p. And you know what? I think we actually have our rectangle code might actually have all this stuff in it already, because I feel like we did this. We have our inverted infinity rectangles here, but they're only for sorting in 2D, it looks like. We never did the 3D version of it. Yeah, so we never did the 3D version of these, it looks like, which I'm not sure why. I would have thought that we would have, but it looks like we never had a need for it. So we have like a rectangle 3. Does it even have a union function? Yeah, we didn't, for some reason, we didn't even have a union function for our rectangle 3, and I don't know why that is. That's unfortunate, but I can just add one. Yeah, I mean, you can see here, we have like a very few, oops. We have very few of these. So that's unfortunate, but I'll go ahead and add it anyway. So really, you know, this is just a case of having one more thing to iterate over. So you can see here we've got, you know, x, y, z's, and all it's doing is just taking and making sure that you always take whichever the furthest is in any direction. So the lowest x, the highest x, lowest y, highest y, lowest z, highest z, and that produces a rectangle that encloses the two rectangles that you've added. And so all I want to do here is if I go through the first actual box and the actual box count here, and I just create one of these rectangle 3s. We'll do this in a second. So center half dim is exactly the kind of rectangle that we're talking about here, where we have a P, and make this root box. Okay. There we go. And so when we go ahead and create this, all we have to do is use the bound. So I can do get center on this bounding box, and then I can get radius on this bounding box. And so this will just loop over it, do the union here of whatever the box we look up is. And I think that gives us what we want. So all we need is this the inverted infinity rectangle, the magic inverted infinity rectangle, and that's just one that is has like literally infinite opposite directions. So it's like the encloses nothing. So anything that you put into it, it will immediately snap to that when you do a union, and then it will keep growing from there. So we want one of these, again, for rectangle 3, which we can do really trivially. It just involves adding one more of these to the mix. All right. So I think that's all we need. Oh, it looks like, oops. It looks like these actually use actual vectors here, which makes sense. Not sure why the other one doesn't. There we go. And, okay. So we may have called this get halved in. Not sure. Or maybe there is no one of these. Let me add that as well, because I'd like there to be one of those in rectangle 3 as well. So we've got where's my rectangle 3 code? Yeah, so for whatever reason, we never had a get radius. We only had getting the dimension. So let's go ahead and do that. So there it is. Does not take one argument. I agree with that. Do we not have safe truncate? Oh, whoops. 2U. Yeah, there we go. All right. So, back to business now. So once we know what the bounds are for this thing, then what we probably we want to add in the references here as well. So for each box, I think we want to do a adds box reference, like so. And so we go through here adding the references in. We go ahead and take the union of this box with our global box so that now we know we produce the root box's size as well. And then we call split box on that box, right? And we're going to go ahead and do the whole thing. So we do root box, first child index, root box child count. And you know what? Maybe we don't even do that. Maybe this just doesn't have anything in it yet. You know, or maybe it just doesn't. Yeah, maybe that just doesn't have anything in it yet. And we just pass these in. First actual box count. So we come in here and say, all right, do those two. We add these box references. And we want to assert here as well that the solution box ref count equals 0. And then at the end, it equals the actual box count. Because again, we just want the first block of these to line up. And in order to do that, also, I guess the root box here has to be added after we do that, because the root box is going to be after those initial guys are done. So that's right here. Yeah. So maybe we just do it like this. So we say, all right, coming in here, we want there to have been no box references added because there's been no hierarchy set up yet, and we want that to be true. We then say, okay, let's go ahead and snap a copy of how many boxes there are at the outset. Those are our actual light boxes that are not hierarchy, sorting nodes or anything like that. We go through them all and we say for each one of them, let's add a reference to that box that just makes them be 0 to whatever. And we union in their size, so now we know how big this box is. We then say, let's add our root box, because now we know what it is. And then let's split this root box in half so that we can split it into at least two pieces, so it can be broken up in that way. So again, we don't know how many pieces we want to break them into. We could also break them, we could also do more of an octree where we break it into 8 chunks. Right, if we wanted to. So it's really hard to say how we want to do that. We could do it either way, and I don't know. So we're going to find out. So when we do split box here, here's our split box call. And what we can do now is say, all right, this is going to give us the box that we're trying to create because we've got one for it. And it's going to give us the range to go through for boxes. Oh, and it should... solution root box, yeah. And then we were sort of saying we'll pass the dimension index, which in this case will just be 0, so start with the x-axis and it'll be fine, I guess. Okay, so then what we want to do is we want to be able to split things into 2 halves based on which side of the thing maybe their center lies on, let's say. So what we're going to do here is we're going to do that loop over the sub boxes, and so it's going to be very similar to this, but it's not going to be quite exactly this, right? That's going to be just slightly different, and then we're going to go from there. So what I want to do here is I want to loop over, this is the first ref index, and this is the ref count, basically. So we're going to loop over first ref index, and we're going to go to... this is our box reference. We're going to go from the first ref index to the first ref index plus the ref count, like so. And we're going to classify each of these by where they are at the moment. Now, there's different ways that we could try to do this. One of them takes more storage than we actually need to use. So we can talk about ways that we could avoid doing that, and let's just go ahead and look at how this is how this is going to unfold and what we might have to do here, just so everyone's on the same page. So spatial. Partition in place. So what we want to do here is say, all right, let's say we've got a region like this box, and there's a bunch of stuff in it. And what we want to do fundamentally is split it into 2 halves. So we want the things on one side in one half and the other side in the other half. And saying half is wrong here because it may actually be lopsided. Who knows? We're not even guaranteeing halfness here or anything. So what we want to do is we want to go ahead and say, what is the way that we will track where people are in this so that the next time we call it and we say split this one into these 2 halves, we know which elements we're splitting, right? So we know how to track on the way down. Well, what we've got at the outset is we've just got an array that has a reference to each of these, like number 0, 1, 2, 3, 4, all the way to the last one. And what we're going to do is we're going to loop through these indices and say, okay, box 0, which side is it on? Now, the problem that we'll have is, if we see that it's on the inside, the one that we're going to keep as the first set of indices, let's say, then we would be fine. But if it was on the outside, we don't have a place to put it, right? Because we don't know how many indices there are. So if this was not supposed to be here, how would we know what to do with it, right? We wouldn't. So that creates kind of an interesting dilemma for us. So one way we could do it is say, well, if it's supposed to be in, we just skip it because it's in the right place so far, right? And then we go to the next one and we say, okay, is this in the right place? No, it's not. Then we remember that we could put something here, and we continue on, right? Then when we find something that is supposed to be in, we move it down, right, to the next one. This is not a particularly efficient process, and it's kind of ugly. And it's exactly like the old, should you merge sort in place or not? And the answer is you can do it, it just becomes really onerous. So what we probably want to do, again, is have some kind of temporary buffer that we just use that we can ping pong between, right? Where we just write our indices into it, and then we only do our add refs on the very end, right? That seems like a saner way to do it to me. Rather than having to use this as temporary buffers. Because it'd be pretty easy for us to just have two large scratch buffers that are just sitting around not doing anything. That's not really very costly to us. It's pretty simple for us to do. So, for example, if we wanted two of these here, like something like this, where we could pass those down, that might be a more interesting way to do it, right? And then only when we're actually 100% positive that we are done with our splitting, then we will actually add the things, add the boxes to the list, right? So that seems a little more compelling to me. That seems good to me. So let's just assume that we're going to do that. So let's go ahead and slightly modify this routine. Instead of calling add box reference, we're just going to use, and in fact, that actually makes one nicer thing, which is that we don't have to do any assertions on the box ref count now. We just don't care. Because even if there were existing box references in there, this will still work. So what I want to do here is say, okay, we're going to start by saying that scratch A is the table we're going to start with. So we say that scratch A box index equals box index. And this first actual box thing is not really that necessary anymore. It's just this, right? So that should be fine. So we go through here and say we go from 0 to the box count. We add all of these in. Then when we actually start to go do stuff, we don't care anymore because we're never going to look at that again. And when we come through here, we just say like, okay, here's scratch A and scratch B. And we know the actual box count is the number we're doing for scratch A. Go. So once we call in there into splitbox, then, so this is slightly different. What it's actually doing is it's saying, okay, we've got a source and a dest. Oops. Hello, caps lock. And a count. And that's all we need. So now we come through here, we say, all right, we don't need to use box refs anymore, so that's kind of nice. So we can just use box index, or I guess it's sort of scratch index or source index. That's, I guess, what it would be called. So going through our sources, we know that we start at 0 now, and we know that we have a source count that we've been passed. The boxes, as they come out, are just references to the boxes based on this source value. So the source is going to give us the box to load. We can load that box in, and we can process it as necessary. So the way that we're going to do this is we're going to write into this the scratch buffers and pass those down in some kind of nice way, right? That's our goal here. Okay, so let's figure out a good way to do those two partitions. Shouldn't be too difficult to figure out how to do that nicely, so let's do that. We probably want to do a thing where we've got two different rectangles here. So we've got a rectangle 3. For A and B. And then what we're going to do is we're going to do a classifier here to figure out whether we're in A or B. And we'll talk about what that's going to be in a second. And we're just going to say, all right, bounds A and bounds B are both going to be tracked separately. And they're going, whichever one of them is supposed to get it will get the box. Now, if we want to be, if we were going to be super cheeky here, we could actually put the ternary operator on this, but we're going to have other things we want to do in the if statement, so I'm going to leave it as an actual if statement. Okay, so we're going to expand one of the bounds, depending on which one it is, and then when we're done, we're going to do a split box call for each of the separate children that we're talking about here. Like so. Don't ask me why I put that there. That's not what I meant. Okay. So what we want to do now is we want to pass down subregions to these guys. So we know we need to have something here that's like count A and some array here. And then we need the sort of swap space for this thing. We don't know what this is. And then we know we've got like sort of a next dim index that's got to get passed here. And the next dim index is pretty simple. We know we only have 3 dimensions, so the next dimension index is just whichever the next one is. So it'll go x, y, z, x, y, z, x, y, z. So this will sort of be like a KD tree at first. It's not quite a KD tree because they can be a little bit overlapping, but it's, you know, it's similar to a KD tree, right? So we will play with that in a second, and at the moment we're just going to leave it as is. All right. So here in child A and child B, we've got to be able to do our sort of same call we were using to add boxes here. So you can see we add box storage for these two, and we add a box for them. Once we know what the child box is, then we have to actually initialize it. So we have to say what its bounds are, for example. So we know that its p-value is the center of bounds A, and we know that the radius is whatever the radius is for bounds A. And the same is true for box B. So from there, we now have to sort of start to figure out how we're going to build these arrays, because there's not much else left to do. There's a split plane, which we have to figure out. And then there's the way we're going to actually align these arrays to work properly. And that's a little bit harder. We probably need to pass one more thing down here as we go, but that's sort of a separate issue. So what we need to do now is every time we do these, let me put here, we're going to need to count B and array B. There we go. So there's a couple different ways we can do this, right? And we have to kind of figure out how we're going to make it work. We know we sort of have a destination buffer that we know we've got 2 buffers, one that we have to read out of that tells us what's going on, and one that we're trying to prepare that we can write into, right? So when we come through here, if we were reading out of the source, we can't touch it, but we can do anything that we want to the dest array. And we know how big the dest array is as well. So what we could do is write to the top and the bottom of the dest array, and that would probably be fine. So yeah, I think that would just work. Since this is going to recurse, though, we've got to, it's pretty tricky where we place these, because when we call it again, it's exactly like merge sort. So do you remember our merge sort? How this thing worked, right? It did the two like calls on the way down, and then it had to do this sort of copy out, and we just decided not to ping pong, I think, at that point, because it was too complicated, and we were like, let's just leave it simpler. It's exactly like that. It's a pretty tricky function to figure out exactly where we want these things to go. So as we push them down, we can take less space to do it in, because we know ahead of time how many we have. So we know we can do it in the subset of the array that is the actual space we were previously using. So that part's not really a problem. So let me see, let's just see what we can do as far as ping pong. Let's just see how it goes. I'm not sure. So if we go ahead and say we're going to line these two things up into our output array. So we know how many there are in the source count. Therefore, we know that the dest will only have this many in it, because we can only we'll only ever write as many as we had total. So if I have two counts here, here's my count A. I guess this is U16. Count A and count B. I start with both of those being 0. Then what I want to do is say, in the case where I hit either of these two things, I'm going to increment them because I've got a new one in that bounds. And what I want to do is I want to place the reference, whatever reference this one is, and I should probably snap that reference here. So here's the box ref. Right? That's the reference to the box, whatever value it actually is. So I want to place that reference into the destination at a particular location. So in the case of A, I probably want to say, okay, it'll go into that box reference, oops, sorry, will go into the bottom of the destination array going upwards. So it'll start at 0, go 0, 1, 2, 3, 4, 5, 6, 7 as things go into A. If things go into B, we can go from the top down. So we could say, all right, dest count B as a subtraction from the source count -1, right? So we start at the source count -1 element, the last element in the array, and we go backwards by count B and store them there. And as we go, we just count B backwards, so we're like fill them in backwards from that top, and then at the end we have our array sorted into 2 halves, right? So once we have our array sorted into those 2 halves, then when we come through here to make them go, what we know is that the destination, if we use this source here, we know that our entire source array can now get destroyed because we've moved things into the dest where we don't need them anymore. So the source array itself is now completely erasable. So what we should be able to do is pass the source array as the destination, because it's not useful to us anymore, I think. I believe that just works. And at that point, we're pretty much done. All we need to do is our classifier and one other thing, which is the termination condition. So let's start with the termination condition. So let's suppose we come in here and source count is less than the minimum source count we want in an area. So let's say that, so let's say that we want no more than 4 boxes, but if there's 4 boxes, that's a plenty. So that's plenty small enough. So if we are entering split box and we have 4 or fewer boxes, then what we can do is say, let's make this an actual box that stores like sort of a leaf container, right? It's going to contain the actual boxes themselves. So at that point, what we do is we say, all right, The parent box is now a real box, a real terminator of the tree. So underneath it will be only actual boxes. It will not be sub boxes anymore. And we'll actually just store those boxes in here directly. So what we want to do is say that the child count equals the source count. We want to say the first box index equals whatever the current box ref count is. And then we just want to add box references for this source here, right? And so maybe we'll just have a call that adds box references in bulk, like so. In fact, maybe we do it like this. And if we look at what a lighting, oops, that's good. If we look at what a lighting box has to have in it, we can see here that we've got P and radius. Those will already have been set by the parent routine. We have transparency, which is not relevant for a parent box. Latencies, not relevant for parents' boxes, at least not yet. Child count, first child index, they're going to get set. And then we've got the pad there, which we don't care about, right? So this should do it for there. And that leaves us just with the classifier. So what I'm going to do with the classifier here is I'm just going to say we've got two things. We've got the direction vector for classification. So here's the, let's say, class direction. And what that's going to do is that's just going to say, okay, the classifying direction. In fact, again, like I said, this is actually going to be trivial for us to do without a switch statement, so I'll just do it. So the classifier's direction is just going to be 1 in whatever direction the dimension index is, right? So we're just going to say, all right, if the dimension index is 0, the classifier is 1, 0, 0, right? It's the x-axis, it's the y-axis if it's 1, it's the z-axis if it's 2, and it can't be 3 because we're going to wrap at that point. So that gives us our classifying direction. And then what we want to do is we want to take whatever this parent box's P value is, so the center of this box, and we want to say if you're on one side or the other of it, that's going to be the classifier. So what we want to say is just, okay, the inner product of this P value of the center of the box with the classifier direction, that's the classifying dot product. Like that's the classifying distance, let's say, right? That's how far you have to go before you're on the other side of the classifier, right? Then what I can do is do the same dot product and just say, okay, if the inner product of the classifying direction with this boxes, the test boxes P, if that's less than the classifying distance, then you end up in your A range, otherwise it's in your B range, right? And that's it. So that's really all we need to do. There's some fat in here that I can, even in this thing, we could say to do, Casey, don't produce child boxes that aren't full. So, you know, what we could do is put a special case in here that don't have members. So, you know, if count A, and I guess, you know, there's no reason not to just do that now. So if count A is greater than 0, we process this path, right? If count B is greater than 0, we process this path, right? So, you know, don't bother going and creating an entire classification box for something that doesn't actually have anything in it. Because if all of the things went in one side, then we can just forget that classifier and try a different classifier. The only problem with this process is we don't have a way to bottom out on it yet. So in theory, the problem we would have here is we need to know that at least one thing will get split, or we can get in an infinite loop. And I'm really just not sure how to do that at the moment, unfortunately. So if you have a bunch of boxes that all have the same X, Y, and Z position, so they're right on top of each other, and then they'll never get split, right? So I'm not sure exactly what to do about that. You need like a fallback case that catches when you have ended up in that situation. But I'm not really sure what it would be. I think you just don't split it. Basically, if you've tried each split and you didn't split at all, then you just give up, I think. So you know what? I think we can do that here. I think what we do is say, so I think what we do here is say, all right, look, we're going to assume that if something has more than 4 elements that we will be able to split it. What we'll do is we'll say, while it's splittable, so while we still think that it's splittable, we're going to do this loop in here. And what we will do is we'll check in here and we'll say if count A is not equal to is greater than 0 and count B is greater than 0, then actually do a subsplit. Otherwise, keep trying, right? And you know, maybe what we'll do here is even say, okay, for attempt 0, attempt is less than 3 plus attempt. So something like, in fact, you know, the other way we could do this is say, something like this. So we'll say that splittable is false. We'll say if the source count is less than or equal to 4, splittable equals true, else. In fact, I guess we'll just do this. So we'll assume it's splittable. If the source count is greater than 4, we try to split it. And if we split it, we set splittable equal to false, and we break out of the loop. That'll work. Right, we break out of the loop, and then we fall through here, and we see if it's not splittable, then we do this, right? So I think that works okay. We could even do this a little bit reversed. Just say was split equals true. Or I guess was not split equals true. That's what I actually want. Was not split equals false. So we assume that the thing was not split. If we did split it, then we set that to false so that this will not execute, right? So I think that now will handle it so that we attempt to break it on all 3 axes. If we don't break it on any 3, we're just like, all right, it's just what it is, right? So that seems pretty good. Here's our classifier. We classify, then we do our split, and off we go. So all we really need is this add box references thing to actually work here. And then I think we're good to go. Now this routine needs a little bit more. because remember, we need an actual parent box here that can have references in it. So what we want to do here is make these references actually be coherent. And so what I want to do is actually go ahead and say child box a index here, child box b. We'll actually just have these at. So what I'm going to do is add box storage here. Directly, and add box reference in this case is not what I want. I just want to get these things to be exact lookups. So now I have the two references that I want to store. So now what I do is I'm going to say add box reference, add box reference. So we know that there's two of these. I'm going to add the two box references in. In fact, I guess I could do add box references to So in this case, I'm going to say, all right, I still need to do this, right? And in fact, now that I look at it, I guess what I could do too is this could actually just, this could just be this, right? Because now what I could do is say, well, the source count and the source are just the correct things to add normally, right? And in fact, I guess I'm allowed to destroy the source array as well, because the source array doesn't get used for anything else. So actually, I guess I don't even need that. What I can do is say, when we come through the source array here, we know the source array was greater than 4 to begin with. So what I can do is just destroy the source array, actually, get rid of this and say, all right, all I really needed to do was say that the source count now equals 2, and that the two first things in it are going to be child box b a at and child box b at. Right? So this now becomes always correct, and the only difference is here is whether or not the child count is overwritten, or whether it's overwritten by the splitter, or whether it just uses exactly what it was passed, right? So I think that's relatively fine. Don't ask me why that was a colon there. That's just a shift key issue, I guess. Let's go ahead and compile this here. So in this case, array A and array B are just, they come out of the counts, right? So array A is actually always the destination. We can see that here. And array B is always the destination plus the source count from A. So those are pretty easy, I think. That's supposed to be first child index. And so what we need here is, we've got one other issue, box index. There we go. So all we really need is the way to do the add references, which we can just make here. So here's add box reference. So make it add box references. And so what we want to do is say the result here is going to be whatever the box ref count was, the box ref count gets added by the count, and we have to assert that the box ref count, like light data width, or I should say the array count, for the box table, plus the amount that you want to add, or I should say minus the amount that you want to add. Yes. Well, I'll do it the other way around. So the box ref count here plus the count is less than the array count. Right? And I can prevent wraparound here if I want to in the test by just making it be slightly larger. So if the box reference count plus the count is going to be too large, then we'll get an assertion here just so we know we haven't overflowed anything there. We'll grab it, the result out. We will increment the total reference count, and then we'll copy. And this is literally just a copy. Oh, I guess you know what? I should do it like this, because we've got to do two different accesses here. So that's the copy there. And so this is a fairly complicated routine here. So we're going to have a lot of issues with it. And we want to try and get it down to something where we can verify it a little bit better. So yeah, this is going to be a bit rough. We'll step through it once and see if we can clean it up a little bit. But again, anything where you're dealing with all these indices and arrays and moving around, it's pretty easy to make mistakes. So it's going to be a bit of a nasty routine to get working properly. That's just the nature of the beast, and that's okay. Ugh, excuse me. So, first thing is first, let's go ahead and get a breakpoint in where we want to be here. There we go. There we go. All right. Oh, and the other thing I would like to do is let's go ahead and turn off the debug. There we go. So looking through here, we start off by saying, how many boxes do we have? The answer is there are 77 of them. We make bounds that are basically including the opposite of everything. The opposite of everything. It sounds like a bad novel. So what we do is we loop through each of our boxes and we say, all right, we're going to start by taking whatever the scratch A array is. You can see there's nothing in it at the moment. We're going to widen the bounds to include whatever this is, and we're going to write the first index in there, which just happens to be 0, so you don't see it happen. And now we've created a bounds that just include just that first box. Then we're going to go to the next box, write the index in, and then widen the bounds again. And we're just going to keep doing this as we fill up this array. When we get out, we're going to have an array that goes up to 77. As you can see, the 77th entry, it stops there. So we have 77 boxes, 0 through 76. And all of the boxes should be included in these bounds, which looks like roughly they do, so that's good. We're then going to create a root box here, which is what we're doing like this. We get the root box index, and that index is 0, as we would expect it to be, because it's the first box that has an actual positive reference to it. We then go ahead and get that box, which gives us back, hopefully, our root box, and we set its p value, p and radius values. So here's that root box. Oops, that's good. I didn't want to launch an In what universe do you think I wanted to launch an HTML window out of here? I have no idea. Don't ask me, ladies and gentlemen, Microsoft Visual Studio. Okay, so in here we've got a p value and a radius value. That radius value looks about right, because you can see that this appears to be about -6 to 6 and about -3 to 3, which is exactly what this radius would indicate. And it's got very close to 0 as its center, so that's all good. We're then going to go in and try and split this thing. We're going to pass the scratch A as the source. So we come through here and we look at the source count, which is 77, and the source array which has all of those indices in it, and we looked and see that it's greater than 4, which is exactly correct because it's way greater than 4. We look at the classifying direction, which should be 1 along the x-axis and is. We look at the classifying distance, and that's 0, which it should be because it was a fairly balanced, it was -6 to 6, so it's 0 was about right. And then we create bounds for A and B that include nothing and counts for them that include nothing. We start with our first box reference, and we grab out that box, and we look at what that box is. Here it is. And we looked at the box reference. I think that's correct. All looks reasonable. Hard to say for sure, but nothing jumps out as being wrong. We take the inner product versus the classifying distance, and we see which side we're on. In this case, we're on side B of it. And does that make sense? Yes, because we're looking, this is greater than 0. Less than 0 would have gone into here. So then we're going to add to the very end of dest. So if we take a look at dest 76, or I guess we can just look at 77 worth of dest, what we expect to see is this add to the back end. So we expect it to be added here. Of course, I guess now that I'm thinking of it as box 0, we wouldn't know if it was. So that's I should have probably written a garbage value into there first just now so we could verify that it was, but oh well. Now box B should get widened a bit. I don't know if we ever looked at those bounds, so here's bounds A. Why did they stop advancing to the next one when you hit return? I just don't understand it. It used to be so easy to use for that, and now it's horrible. Don't understand it, but there they go. So there we go. That expanded box B to include it, and now we've got increment of box count B to say that there's one in there. We're going to classify the next one. That one also went in here, so now we should be able to see that get written in here, and it does. Expand again, and off we go. It looks like we're writing most of that side. Now we're going to write in here, so we should see that box ref getting added here. It does, and off we go. Let's go ahead and jump to the end. What we should see is this whole thing should now be filled, and it is, so that's good. We should have a count A and a count B that, if we're lucky, are pretty similar, and they are. That's not too bad. That split, you know, that's a reasonable split. It's not perfect split. A perfect split would be half and half, but it's, you know, pretty darn close. So that's good. We go to the next dimension index, like so, and we look to see whether we got counts. We did on both cases. So now we're going to add box storage for these child boxes. We're going to split them and see what we get. So here's our child box A. Our child box A looks reasonable to me. We're going to go ahead and split that. And this array should remain probably unmolested in the range that B counts on. So that's what we really want to focus on here. So count A was 34, which means we're looking at this value right here. When we run this split box, we hope to not see any of that get modified, and it's not. So that's real good. So then we come through here, and now we're going to rely on these being valid. They are, and then they change out from under us, which is fine. And then we're going to write these two into our source array. 78 and 145 are our two children. Oh, our break statement. Our break statement's gone. So we found a bug. I accidentally deleted the break statement there. This needs to stop. Once it has a split, it needs to stop. Sorry about that. One more time. So what should happen now when we split two of these guys, we go to the break statement, we record the child count, whatever it was, and we record the first child index as whatever, wherever it was able to add that reference. This says that the first child index was 9. I'm not sure that that is correct, because the first time through Splitbox there shouldn't have been any. Oh no, there could have been, because you could have hit this case without splitting. So that seems okay. So all right, so now we're doing those splits, yeah. So we're not quite working here. It's that's interesting. So we've got some definite bugs happening, but they're not It's not a full bug. It's like the initial split is wonky or something. So I'm not sure what's going on there. That's pretty weird. But that's okay. So what we want to do now is start debugging the actual splits to make sure that we split this thing correctly. And that's easier said than done because it's kind of hard to draw these things sometimes. But what we want to try and do here is maybe get a mode where we can actually draw some stuff that indicates to us where these things are and what the splits were, so that we can go from there. Because what we don't know yet is we don't know whether or not... Also, one interesting thing about this is you'll notice the run speed. It's running at 30... It's running at almost 60 frames... I mean, almost 30 frames a second, but it's not in optimized mode. Right? We had it in debug mode. So hey, if we got this working properly, I guess the reason it's running faster is because it's only doing half the lighting, though. But yeah, compute light propagation taking a lot less time now. I guess that's probably, though, probably not because we did a good job speeding it up yet. It's probably just because it's not actually doing the correct light propagation. Anyway, so the problem that we have now is twofold. One, we don't really know how we're splitting these things or if we're even splitting them correctly. So we could just be producing a bogus tree that's all messed up and who knows, and it would be easy to imagine that happening because our indices, we have all these indices and stuff running around, and it becomes kind of complicated, right? So we don't really know what's going on there. And furthermore, we have a secondary problem, which is that we don't know if the raycaster is working properly. Because we only ever tested it with just one spatial node that had two nodes below it. That had all the nodes below it. So for all we know, we could have produced a very good split that actually is constructed properly, and our ray tracer is just screwing up. So we kind of have a nasty problem here of we don't actually know who screwed up, and that's a problem. So let's go ahead and see what we can do about that. This routine was not necessary anymore. There you go. So yeah, so what we're gonna try and do here is get this code, try to figure out how we could draw something or inspect this code in a way that would allow us to know that it was working somewhat correctly. And then the other thing we have to verify is that this code out here is also working properly as well, right? So hopefully that's the case. This is looping over points, so that's not really a problem. This raycast is working on boxes, so we have to go verify that's okay. When we actually get the boxes back, it gives us a pointer, so hopefully that's fine. And we never really ask for those boxes again. So in raycast recurse is really the place that we care about here. We go through these child indices here, these for the source, and we ask to get the box there, which should do the dereference for us. Everything else looks like just works fine. If it's got a child count, then we recurse again using that box. If it doesn't, we record the hit. That seems reasonable. It's not a great way to do it, but it seems reasonable. So when we actually... Okay, so I know exactly what the bug is. So the bug here is that we're not actually using the... We need to do the interior check. We need to do the check to see if we're inside a bounding box. So this little cleverness here is not going to cut it. So let's go ahead and back that out. We need to fix that bug first. That's just a bug. My cleverness was too clever. I said it might be too clever, and it was. So let's go ahead and fix that. Where is my... Yeah, so when we do it on the root box, right? That's our first one. We loop over everything in the root box. The box you're in, you'll never hit it with array because you start off inside of it. So that's why it was only checking the side that we weren't on, because that one would get hit by the ray eventually, right? Yeah. All right. So let's try this again. So what we want to do here is say, okay, when we loop through these in our raycast, we need to do a check for that. So we come through here. We do a check to see whether we're hitting it. What we want to do instead is make this be make there be two ways to check this. So in this case, this is the case for something that we're not inside. And we need another case for things that we are inside. So if we are inside a box, we would just have to raycast recurse it. So we need an if here. We need one more if, unfortunately, which is not really what we want, but that's just what we're going to have to do. So basically, I guess, you know what? I guess the way to look at it is more like this. Well... Okay, no. This isn't as bad. It's not quite as bad as that. So what we want to do is actually do it here, right? We want to say if box child count and inside box. We do something other than what we're doing right now. So if the ray origin is inside the box, then we have to recurse this box no matter what. Because we don't know when we hit it, right? We could hit it at any time. So I think that's the only real change we have to make here. So if this is a box that has children, and we are inside it, we have to consider its children automatically. We can't raycast it. Otherwise, we can raycast against it. So the question here is, for this light box, what is the inside box call for that? And in order to check that, we need to do something like box p box radius. And I feel like we had a function for this. That we never really pulled out and should have. All right, not really. So, all right. Inside here in the rectangle 3 stuff, I want to do a thing that's like an is inside rectangle, where we basically pass, you know, a p, a radius, and a test. So this would be is inside rectangle center half dim sort of a thing. And then we would do a test here to say, all right, relative equals test minus p. So then we know that it's it's centered around the origin. And so then what we can do is just use 3 absolute values to test it versus the radius. So I hope you can see what I'm doing here. I'm just essentially using the fact that once I make the point that I'm testing relative to the origin, I am in a situation relative to the origin of the bounding box. Oops. Like so, I can just test it versus the radius to see whether I'm inside, right? So that's all I'm doing there. So I don't quite know if that's going to fix us entirely. Looks like it sort of did. We still have a long ways to go debugging-wise, so I'm not going to be particularly excited about that yet, but at least that fixes the basic problem. If we compile in optimized mode, well, one nice thing we can say is we're down to looking sort of 60 frames a second-ish here. Not quite there yet, but it's better than it was. So that's kind of nice. And so we're getting closer, I guess, than we were before. And let's go ahead and take a quick look too at what we can do, how bad we are off of our game here. If I set this up to something else. All right, so here's a more realistic scenario for the game that has a lot more entities in it, as you can see. And, we're getting within striking distance, actually, right? This is not an acceptable frame rate, but it's even sort of playable, like I can control the character and stuff. So that means we're not that far away. And you can see that it's actually doing lighting everywhere, like literally everywhere. It's like you got bounce lights on the ceiling and everything. So there's no trickery here. It's just doing its thing. It does look like there's some things that look a little buggy to me. Like I'm not sure that should be lit right now. Maybe it should be, I'm not sure. But so we may have some bugs lurking in there. Like I don't know, like that. So I'm not sure. So we probably have some more work to do. Our indices, we may have a few things messed up where we're not tracking indexes properly or something like this. So yeah, but getting there, because now we're running lighting on literally this whole thing here, and it's not an impossible frame rate to conceive of getting down to faster. So I think we can go ahead and improve our stuff more from here, and we should be able to maybe get to a place where this is all right. All right, so we'll pick that up again tomorrow. Not tomorrow, next weekend. For now, we can do a Q&A. Jackson Bannon, yes, I love sushi. Oh, wait, we've got 30 minutes still Q&A? Wait, but it says it's 1:15. Isn't that the time? When did I start? I thought I started at 11 and did a 15-minute countdown there. I could be wrong about that. Brian, this is a generic question, but for example, add box storage demonstrates this. I see asserts are used to find exceptions in debug mode. What would be the way to handle a failed assert in release mode, assuming in release mode it is just stubbed? Is it a case where most, if not all, problems would be found during testing and not needed to make changes for release? So asserts are only for things that you are sort of stating you will never allow to occur in release mode. So things that are kind of possible to happen in release mode, but just unlikely, you don't really want an assert for. You want an error handler, right? So generally speaking, release mode asserts, eventually get compiled out. We are actually leaving asserts in release mode, I believe. And it's actually these two things that would turn that off. So technically, this is the mode that doesn't have any asserts in it. Right? So this is actually an assert-free mode. This is what a gamer would actually get on their actual machine or something, right? So there's different meanings of release mode. You can often have assert still compiled in release mode. And so if you take a look at assert and what that actually is doing, you can see it here. It's actually not predicated on whether it's OD or O2. It's predicated on whether handmade slow is set to 1 or 0. So hopefully that makes some sense. What was I gonna say about? Oh, one thing that I think we should have done, I forgot to do, is inside the lighting code, what we should do here is the timed function for compute light propagation. We should also take a look at what the cost is for build spatial partition. Because now we've got, sort of two things that can take time. And so now we can sort of see like, hey, that spatial partition actually is pretty free. It just doesn't cost much compared to anything else we're doing. So that's good to know that it's not wasting any time, right? But it's good to verify that fact. So we know that we're still spending all of our time raycasting, which means we can spend more time building better spatial partitions. And that won't be something that really wrecks us performance-wise, which we kind of need to know, right? All right, next question. Couldn't you have just used a stack or a queue to do a depth-first search or breadth-first search? You init the stack with the root box, and then splitting just adds to it. If the stack is empty, you're done. I'm not sure what you mean. Like, use it for what? So that you don't have a recursive function? Right? Are you talking about removing the recursion or something else? Brian, will we need to go through each assert call and eventually add ways to handle failure cases, or only when we run into an issue down the line and fix those specific failures? I ask because I add asserts to my code, but then wonder what the proper way to handle failures. No, so I guess what I'm trying to say is if you're adding an assert somewhere where you could actually fail, that's not an assert. Like that's an inappropriate place for an assert. Asserts are for things you don't expect to fail. So we don't expect to handle more than 64,000 light sources. We're just saying the game is not meant to do that. And if you make something where it does that, that's an error, right? We're not going to handle it, period. If instead we were saying, well, sometimes you will, and we just want to warn you that you've done that, then that's an inappropriate place for an assert. What we need to do is have an error handler that just clamps the value, only does lighting on 64,000, and then it puts up a little icon to say, hey, you've made a level that's too complicated, right? Or something like that. I noticed how you barely have any code keyword highlighting in your editor. Do you not like that? I don't know. I'd say I have a fair bit, right? There's like all of that is all highlighted. And comments and constants are. So there's a fair bit. Jackson Bannon, do you wish you never started a sushi game thing? Yes and no. So one of the problems with the sushi game thing is that I did all the artwork myself. I feel like that it would have been cool to not do that, I guess is what I'd say. I am a lot more capable in terms of making art myself now, but I just shouldn't have bothered. And probably the game would have maybe come out good if I hadn't have bothered, because I could have spent my time learning to be a game designer instead of that. And then I could have made the game be fun, you know, maybe. So the problem is I think you have to kind of pick and choose what you actually want to do. And I think probably that part was the mistake. On the other hand, I don't know, maybe I can art direct things better now because I know all that stuff. It's really hard to say. Counterfactuals are hard. You learn a lot from everything you do, and it's really hard for you to know. So I'm not sure. Someone says, like I have here, for example, but I'm not sure an example reference to what. Oh, no, I don't care for that kind of a level of science. That's more than I need. Like, I don't need like function names to be highlighted or something or anything like that. It just gets distracting if you have too many different colors on the screen. I don't find that to be particularly useful anymore. Have you thought about making a stream to recap your code, kind of looking over it and explaining it to catch people up who can't watch it all? Yes, actually, there probably will be those after the project's over. So when we finish Handmade Hero, and we're like, this is the code. It's over. We're not changing it anymore. Then we could do it that like, you know, that's where we could say this is a good time to just sort of go over the code and tell people how it works and why we did it that way. Yeah, let's see. Started slightly late and pre-stream went on for longer than usual. No, we didn't start late. I set at 11:15 and we did the timer, so this timer starts at 11:15. The problem is that we had questions that overlapped, so that's just how that goes. Like, I keep the stream to be 2.5 hours. That's how long it is. So there's 15 minutes of pre-stream. If the pre-stream goes long, it eats into the episode time, and then we have 15 minutes of questions at the end. Can you add partition box visualization, or is that not valuable? No, we absolutely will have to add that. That's why I was saying it's a little hard to do, because it's hard to draw partitions in a way that's really clear what's going on in them. But we definitely need to add this. And eventually next time we'll probably have to, because we're going to have to start debugging those and make sure they're getting built properly. All right. How close are we to finishing? Who knows? It's a project for educational purposes for, the people watching, so it's mostly about getting educational content onto the stream. And given that, usually I make decisions about whether to go do something based on whether I think it'll be useful in that way. So hard to say. The frame profiler UI, is that custom made on stream? It looks good. Yes, that was custom made on the stream. The frame profiler is kind of awesome, actually. It's really very powerful. So if you take a look at the way it works, is you can actually pause the game profiling anytime. So the game will keep running, but the profiler's data stops updating, and you can go to any given frame and see where, what that frame looked like. So you can actually get, sort of you can look at if there were spikes or something. You can look at what was happening over time as well. You can also look at other things like thread information. So if you want to see how multi-thread was happening, or what was happening on there, you can drill down kind of in that way as well. You can look at frame stacks. So here's the past frames drawn as stacks there. You can kind of see okay, so something happened in here. Input processing went long. Why did it go long? You can drill down into it if there were subregions. You can see message processing, getting the mouse position, crap like that. You get the idea. So anyway, some of those are more useful than others. Mostly we just use the top list because that gives you almost everything you need. The other thing we never really expanded much on. We didn't really try to get it to a place where it's super useful for finding stuff, so we don't really use it much. But in the future, we could upgrade it a little bit and probably make it more useful. But yeah, it's a good profiler. We've never done the memory version of it. We should at some point, probably, because it wouldn't be that hard. What do you think of functional programming? I've been asked this many times, so you should probably be able to find an answer in the episode guide. All right. So let's go ahead and wrap up since there are no further cues, it looks like. Thank you everyone for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along at home, you can always pre-order the game on handmadehero.org, and it has the source code included with it so you can do your own experimentation. That's about it for today. I will be back next week to basically work on the actual optimization part now of getting a spatial partition and a lighting algorithm tuned so that we can try to actually run at 60 frames a second with a full size level in there. And it depends on how we necessarily want to do this. Since you can see the fact that we were able to build the spatial partition on the CPU in a trivial amount of time, that means that one of the things that we could consider now is running the ray tracer on the GPU itself. We do have that option. We don't necessarily want to do that, but we could do that, and so we'll have to start thinking about whether that's appropriate or not. So we'll do that. We'll start making those decisions as well. The other thing we could do is continue to run it on the CPU and just run it on the CPU parallelized and SIMDized, right? So we'll see. That's about it for today. Until next week, have fun programming, and I'll see you all on the internet. Take it easy, everybody.